Imagine a world where the underlying energy of the universe is harnessed to power our cities, industries, and homes. This isn't a scene from a science fiction movie, but a potential reality with the advent of zero-point energy harvesting technology, or ZPEHOT. At the heart of this breakthrough lies the sophisticated interplay of quantum field theory, thermodynamics, and advanced material science. As we peel back the layers of traditional energy paradigms, ZPEHOT emerges not just as a novel concept, but a transformative one poised to redefine the fundamentals of energy use and production. Quantum field theory, or QFT, is more than just a complex set of equations. It is the backbone of modern physics that describes how particles and forces interact at the quantum level. In the context of ZPEHOT, QFT explains the existence of vacuum fluctuations and zero-point energy, which are essential concepts for understanding energy potential in the quantum vacuum. In parallel, thermodynamics teaches us about energy transformation and the laws governing these processes. For ZPEHOT, the second law of thermodynamics is particularly relevant, as it deals with the efficiency of energy conversion systems. Understanding this helps in designing systems that can effectively convert quantum mechanical energy into usable power. Additionally, the role of nanostructured materials cannot be overstated. These materials, often engineered at the molecular level, possess unique electromagnetic properties that could potentially optimize the interaction with quantum fields, thus enhancing the efficiency of energy harvesting mechanisms. The core of ZPEHOT lies in its ability to conceptualize and model energy extraction from the quantum vacuum. Quantum vacuum fluctuations represent the temporary appearance of energetic particles out of nothing, as allowed by the Heisenberg uncertainty principle. This phenomenon suggests a reservoir of untapped energy, zero-point energy, or ZPE. However, extracting usable energy from these fluctuations is not straightforward. Theoretical models, such as those incorporating the Casimir effect, provide a framework for understanding how forces unobservable at the macroscopic level can be manipulated to do work at the nanoscale. Developing accurate computational models is crucial for advancing ZPEHOT. Tools like Skywise.ai enable researchers to simulate quantum vacuum interactions, providing insights that guide experimental setups. Specifically, the Casimir effect, which demonstrates the force exerted by the quantum field between two plates, can be modeled to explore new configurations for energy extraction. Photon harvesting, another promising area, involves capturing virtual photons generated by vacuum fluctuations. Simulating these interactions requires a deep understanding of quantum electrodynamics, or QED, which describes how light and matter interact. The transition from theory to application involves designing materials and devices capable of interacting effectively with the quantum vacuum. Nanostructured materials and metamaterials are at the forefront of this design process, offering properties that can be tailored to specific needs, such as frequency and wave manipulation. Developing quantum resonators, such as optical cavities and plasmonic structures, is also critical. These devices need to be optimized to enhance the interaction with zero-point energy while maintaining structural integrity and performance under various conditions. Prototyping these concepts requires sophisticated fabrication techniques and a precise experimental setup to measure and validate the interactions and energy harvested. Integrating ZPE systems with existing renewable energy infrastructures presents a unique set of challenges and opportunities. Hybrid systems that combine solar, wind, and ZPE technologies could potentially lead to a more robust and consistent energy supply. Furthermore, optimizing these systems involves refining device parameters, employing stabilization techniques, and using advanced energy management algorithms to handle the inherently fluctuating nature of zero-point energy. The development of ZPEHOT is not without challenges. Stabilizing the energy output to ensure a reliable power supply is crucial. This might involve integrating advanced energy storage technologies and developing new control mechanisms to maintain system efficiency. Additionally, the environmental impacts and ethical implications of exploiting quantum vacuum energy must be thoroughly evaluated to ensure that ZPEHOT contributes positively to the sustainability goals and does not lead to unforeseen negative consequences. Through this detailed exploration, we gain not only a deeper understanding of the physics behind ZPEHOT, but also appreciate the potential it holds for revolutionizing our energy systems. As research progresses, the secrets of the quantum vacuum continue to unfold, bringing us closer to a future where energy is abundant, clean, and accessible to all. This essay has thoroughly dissected the intricate world of zero-point energy harvesting technology, ZPEHOT, from its quantum foundations to its potential applications and challenges. By integrating principles from quantum field theory, thermodynamics, and material science, ZPEHOT stands on the brink of transforming our energy landscape. The journey from theoretical concepts to practical applications involves rigorous modeling, design, and testing, aiming not only to harness quantum vacuum energy, but also to integrate it seamlessly with existing energy systems. Each step in the development of ZPEHOT reveals broader implications, not just for energy production, but for the fundamental understanding of the universe. As researchers continue to push the boundaries of physics and engineering, ZPEHOT might soon move from experimental setups to a viable, revolutionary energy source, reshaping how humanity interacts with the fabric of reality itself.